Yeah. Yeah. Thank you very much. Yeah, this talk will be about homological mirror symmetry, which will be, in this case, which will be a statement of the following form: the derived category of coherent shifts on certain generalizations of the usual Tate curve. I mean, generalization of high genus is equivalent to perfect complexes on of the Foucault category on certain singular symplectic surfaces, actually certain configuration of spheres, which presumably should be equivalent to the Foucault-Seidel category of the corresponding Landau of the certain Landau-Ginzburg model. But here we will consider certain very non-standard version of Foucault category, which is defined for singular surfaces. First, I'll start with here. Foucault-Seidel of certain, I mean, of the certain six-dimensional Landau-Ginzburg model.
So what's the lambda? TW what?
Where? Here?
No.
Here?
What? TW.
It's just a bracket.
No.
Foucault-Seidel Fs.
Okay.
This is bracket
Okay.
of some Landau-Ginzburg model, some variety with function and with symplexic. No, it's just notation. Z omega W. Oh. I mean, just the yeah. I will not basically. I will not consider Landau-Ginzburg model. I will consider only the critical locus, and everything will be defined in terms of the critical locus of this Landau-Ginzburg model. First, I will describe the B side, which is somehow more standard. So the combinatorial data here will be the following. So we will have G will be a trivalent graph. So which has sets of vertices and set of edges, and to each vertex we associate certain. To each vertex we associate first just a copy of P1, which we denote by YV, and to each half edge. So whenever we have half edge, we associate to it some marked point, some distinguished point on this copy of P1. So, I mean, we have trivalent graph, so basically 3 half edges from each vertex give us, so we require that we have 3 distinct points on the P1. And we will fix some additional data, which is choosing a coordinate near each of these distinguished points, namely, so again for each half edge with shade T E V, which is just an isomorphism between YV and P1, just a coordinate such that such that this coordinate vanishes on the corresponding marked point and takes value infinity at one of the other 2 half edges. Yeah, and also we can make some natural assumptions. For example, that on the third half edge, on the third mark point, it takes value 1, but it's unnecessary. So after you fix this data, we can, and also, okay, so this is the B side data, and also A side data will be K. I will tell it will be Novikov field actually. Yeah, everything will be over non-Archimedean, non-discretely valued field, which is.
So what's the difference of E prime and E?
Just to E prime is just some another half edge. Yeah. And also, well, okay, let me put it here. Another choice will be positive real numbers associated with each edge. So what this means on the A side, we will have so A side. We will have trivalent configuration of spheres, where spheres correspond to the edges and the singular points in which spheres will meet correspond to the vertex. So we have some vertex, and this E prime, E double prime correspond to the edges, and this positive real numbers will correspond to basically the areas of these spheres. Yeah, so I consider abstract configuration of such of this sort, but you should think about it as a critical locus of the of the potential in the Landau-Ginzburg model, and these are symplectic areas. Okay, so as I said, I will define a version of Fukaya category for this singular manifold, but first I will describe the most standard object, which is generalized Tate curve. Namely, it is defined as follows. So first, our base field, I just recall that it will be a Novikov field, and actually we can take the field of coefficients to be not necessarily complex numbers, but just some abstract field. So we're taking the completion of the group algebra of real numbers. If you wish, we define the non-Archimedean valuation by setting modulus of t to the power lambda is exponent of minus lambda. So this is the complete non-Archimedean field, and which is usually denoted by lambda, and it contains lambda 0, which is its ring of integers. And the only assumption which I will make is that the characteristic of the residue field, which is the field of coefficients here, is not equal to 2 or 3. But this is kind of technical assumption. Okay, so how this Tate curve is defined? There are different ways to define it in terms of rigid geometry or in terms of formal geometry, but I prefer the rigid analytic framework. Namely, let us define the action. Usually it is defined. This Tate curve is defined to be the quotient of the projective line minus certain counter set by the Schottky group. But it's actually more convenient here to define the same thing in terms of groupoid groupoid of paths in this trivalent graph. Namely, what we take is the following. So to each v, as I said, we already associated the copy of the projective line, and now to each h.
What is gamma?
It will be. I didn't define it yet. It will be the Schottky group. Certain gamma is isomorphic to the free group on G generators. Say x1, etc. Xg. It will be free group on G generators. Yeah, it's a Schottky uniformization for curves, but not Archimedean version. Yeah, so to each V we associate the copy of the projective line, and to each H we associate the following transformation, which is given. So if this is V and V prime, then the associated transformation from YV to Y, let's denote by gamma, let's say. Gamma E from YV to YV prime is given by just putting so T E over V prime of gamma E of X is equal to T to AE over T E to V of X. So basically, in terms of this coordinate, this is just the transformation T goes to T to AE over T, nothing else. Yeah, but we need to choose the coordinates vanishing at this points, and I choose them exactly in the way which I did this in the beginning. So in this way, we obtain the action of the free groupoid. Now this group will be actually some gamma VV, but let's consider gamma to be the groupoid of paths in G. And we can consider this collection or this data as a factor from gamma to varieties defined in this way, and then we can take one more notation for each copy of each of our copies of projective line contains certain counter set, which is defined to be the set of limit points of gamma VV. So gamma VV is just a fundamental group of this graph at the vertex V, and limit points are just another equivalent way of describing this set is taking the closure of. So you take all fixed elements, fixed points of non-identity elements, and take its closure. Yeah, and then the generalized Tate curve is defined. So one of the ways to define it is just to choose some vertex and to take YV minus this limit points by gamma VV. Or equivalently, you can say that you take the disjoint union of YV over all vertices and take the quotient by the groupoid. It's just the same YV minus this limit points. The shortest way to define it is you take all elements. All elements are actually hyperbolic. All non-identity elements in this group act as hyperbolic transformation. You take fixed points. There are 2 of them for each element, and you take this countable set and take the closure. It's actually the same as endpoints of the certain regular trivalent tree. Yeah, so it's naturally a counter set. And you consider the complement of this set of limit points, and then the Schottky group acts freely and discontinuously. So you can take. So the quotient is well defined. The quotient is actually a smooth curve, smooth compact curve of a smooth proper curve of genus G. This is by definition the generalized Tate curve. And the simplest version of this is actually for the classical Tate curve, which is for genus 1, when you have only one, which is obtained just by taking GM, so non-zero elements, by, say, in our notation, T to the power A all powers. And this is just a special case of this. If you consider, okay, I consider trivalent graphs, but you can consider just a vertex and one loop. And in this case, there are only two limit points, just 0 and infinity. You just throw away. So P1 minus 0 to infinity, just you're getting the usual Tate curve. Yeah, but starting from genus 2, the picture is more complicated, and this was actually worked out by Mumford. But this particular version of Mumford's construction is natural to call it generalized Tate curve. Yeah. So that's what. So this xk is a smooth proper connected curve of genus G. Yeah, and so one side of mirror symmetry is taking Debye-Koch of this curve, and another side. Dim, is it clear? The concept? What? Just a formal variable. I mean, just in the. One, yeah. I'm considering. Yeah, of course, there's a version when you consider a lot of variables. Yeah, just one variable, but we take it to the power of the area of the component here. Okay, on one side we will have this Debye-Koch of this curve, which is somehow a classical object, and the other is not so classical. So for this configuration, so let's consider actually the picture for genus genus 2. Let's consider just 3 spheres attached to each other. First, I'll describe the objects of this category. The simplest kind of objects are given by Lagrangians. Well, in this case, Lagrangian is just a curve. So is given by by circles which don't meet the singular points. So just some circle in one of the components, and of course it can be equipped with some non-Archimedean unitary local system. So if this is L, so L E, E is just local system of OK modules. I mean, free finally generated. No, I'm not removing it. I will explain. This is actually a non-trivial point. Yeah, but first I'm describing the objects. So the simplest kind of objects, they don't meet. And they will correspond to torsion shifts. So they will correspond to on xk. And also, the more sophisticated objects, they will be actually given by configurations of lines so on each sphere we have some line which goes to, some curve which goes from one singular point to another. So in this case, it's just 3 lines like that. So L1, for example, and this no, let's denote it. Okay, L prime, and L prime will be also equipped with some this kind of objects. They also equipped with some again this non-Archimedean unitary local system. No, I'm describing the objects of the Fukaya category.
So this is below
there will be objects in the category on the right, Fukaya of M.
So this is M?
Yeah, this is M. Yeah, sorry. This is singular symplectic surface. Yeah, yeah, but for the moment, before defining morphisms and higher products, I will first I will say what will these objects correspond to. So first, for this, if you have some circle, and let's say, for example, with one-dimensional local system, so LE, where rank E equals 1, then so you have monodromy, which is just an element of just invertible element in OK, and this will correspond to the point in xk, which can be described as follows. So you take if this is v and this is the edge e, half edge, you're taking the point p tilde in this component yv, for which this distinguished coordinate is given by t to the area of this half sphere. So S is the area, t to the s times monodromy. So this is what happens for skyscraper sheaves, and now for more general objects of this sort, which are configurations of curves in the spheres. So we do the following. First, we fix some. Let's fix some collection L0 with trivial monodromy. Of the half sphere. I mean, of this. Yeah. It's preserved under Hamiltonian isotopy. So we fix some collection L0 and just declare that L0 with trivial local system goes to structure sheaf on xk, and then more generally, now if you consider any, let's make the following picture. So let's consider a single sphere. So we have L0, I mean a component of L0 which is in this sphere, and we have some L which can do some rotation in both directions, So we have L with some local system. So the line bundle which we associate with this, so FLE coherent shifts actually a vector bundle on xk. It is given by the following. So first, to define an object on X, so we can actually do it using this quotient presentation in the regional analytic framework. So we can define just a vector bundle on each of the projective lines. I mean, a complement of these contour sets, and then just define the cocycles, the gluing data for each edge, and then what happens is we take actually a sheaf on, so we define f tilde on each yv to be just the trivial vector bundle with fiber EV. So I mean, this local system has a fiber in each of the singular points. So just EV tensor or V, and the cocycle is given by taking phi E, which should be a transformation from f tilde on yv minus fv to the pullback of f tilde on yv prime, and it's obtained basically by taking the monodromy. So this is v and this is v prime. So we're taking monodromy from v to v, I mean holonomy of v to v prime of our vector bundle, and multiply it by the chosen coordinate to the power rotation number of this pair L and L0, and also the Novikov parameter to the power the area between these two curves. So this is actually quite explicit. I mean, because in this short uniformization, you're taking the quotient by the free group or by the free group void, in which, so in this case, cocycles are really easy to define. You can just define them in any way you want on the edges, and this is precisely the correct formula. So this is the formula for this transformation. Now, yeah, and also I should mention here that Falting's theorem actually implies that Falting's theorem of 1983 implies that all these vector bundles which we obtain from these objects are actually semi-stable of rank equals to the rank of the local system, and the slope equals to the sum of rotation numbers over all edges. I mean, rotation number, I mean just the relative. We can always compare. Yeah. So, yeah. So far, I've defined the objects of the Fourier category and describe what they correspond to on the B side. And now no, for things, I mean, he described semi-stable bundles of degree 0 in terms of representations of the Schottky group in terms of certain bounded conditions. Yeah, and actually here we get integer slopes. So bundles of integer slopes, you can reduce them to bundles of slope 0, and then you can just check that the bounded condition is satisfied. I mean, bounded condition is quite tricky there, but in this case, it's not so hard to check. Yeah. So these objects, they correspond to some semi-stable bundles on generalized Tate curves, Tate curve. And now the tricky point is how do you actually define the Fourier category here. And let me define the Fourier differential. So we have L. Let's forget for the moment about local systems. So let's just consider objects L and L prime. In fact, on each of the components, we fix the direction in which our L goes from this singular point, and when we compute Homs, we take slight Hamiltonian perturbations so that L is moved counterclockwise from L prime. So we get something like something like that. Yeah, and each point. So the Fourier complex is given by. So as a vector space, it's given by vector space with basis formed by first by the intersection points. So first summation is over intersection points of smooth parts of L and L prime, and also by the vertices in our graph. So I mean by the singular points. So each singular point gives only one generator, and each intersection point in the interior gives also one generator in the Fourier complex. And the grading on them is for these vertices, we just declare that the generator has degree 0, and for the smooth points, it's as usual. I mean, it's given by the local intersection index. I mean, it's 0, 1, depending on the local intersection index. And here, the tricky thing is the definition of the Fourier differential. And here, the natural question is how do you treat singular points here? And what we do here is we count actually broken disks. I mean, not pseudo-geometric disks, but broken, so degenerate disks, which break only at the singular points. So what happens is, so we have, so for the Fourier differential, so more generally for high products we will have trees of broken disks, but for Fourier differential is just a chain of disks which break at this points, and so this is L prime. So for this disk, we of course we compute them with multiplicity given by, I mean, with coefficient given by t to the power area as usual, and monodromy this is standard. But also there are special coefficients for each breaking point, namely. Once again? I mean that, so we can computing the structure constants in the Floyd differential, and say we're computing structure constants between some x and x prime. This means that, I mean, usually we would consider just the holomorphic disks without anything. Yeah, but here we consider the degenerate configuration, which means that we have configuration of disks attached to each other at the singular points, and yeah, each of these points is some v, some v1, v2, and so on. Yeah, it's some vl. Yes, some. Yeah, but the tricky thing is that you need to add additional multiplicity for such broken disks, namely for each half h, you will, I mean, for each of the half edges participating here. So, for example, we take this E and V1, and here E prime. So we have actually, first of all, we have direction from which we go. I mean, for example, for example, we count so we count the structure constant, which is coefficient of x prime in the differential of x. So we have direction in which we go, and yeah, but it can go along. It can follow some complicated path in our graph. Yeah. For example, some cycle or yeah. Well, I mean that I didn't say where do my x and x prime live. I mean they can both live in the same sphere, or they can live in the different spheres. I mean I'm just saying. I mean describing the general story. Yeah. So here we have actually each component of this configuration hits. So for each of these half edges we have certain multiplicity. So d E prime v1 and d e v1, and so there are certain coefficients. So there are certain propagation rules. I mean, we consider this as a propagation of the disk in this direction, and there are certain rules, and these rules are formulated in terms of constants, which you associate with each such pair. So whenever you have v and two half edges, so you have multiplicity d here and d prime here, and the direction is like this. Then the multiplicity with which you count this situation is the following. It's well, this looks a little bit artificial, actually. What you do is you take one distinguished coordinate and take it to the power minus d, and express it as a formal power series in the other distinguished coordinate. And the coefficients of this power series will be our coefficients. Yeah. This is, I mean, we count each such configuration with certain multiplicity. This multiplicity is the product of local contributions, and each contribution is given by this formula, by power series expansion of the negative powers. So Yeah, this is a little bit artificial, but the point is this: the propagation rules are local. There are some local contributions from each singular point, and maybe there are other ways to choose these constants. Yeah, but this is one of the one preferred choice, and if you do it, if you count the propagation with such multiplicities, you obtain a well-defined infinity structure. So well, here it's mu1, but more generally you consider trees of broken disks, and then I will sketch how do you prove the theorem for this. Do we have some more chalk? Там здесь просто мел такой мелкий. Okay, so now the theorem is proved in the squares to zero. Well, it's some kind of combinatorial consideration. So, well, I mean, usually you do it by Gromov compactness, but here it's the story is more combinatorial, so you can actually do it in terms of just yeah. Yeah, and similarly for general for infinity relations, yeah, it's also can be done combinatorially. Yeah. So sketch of the proof. It's the first step is to show that there is actually equivalence of graded categories, namely if you forget triangulated structure. So you can construct equivalence from let's say cohomology of f of m, and let's take only a vector bundle part. But by this I mean only objects which meet single points. I mean which are configurations of curves. I mean without considering the circles. So equivalence of graded categories from here. Okay, let's say fully faithful functor to semi-stable bundles, vector bundles on xk, but here I mean again graded category. So I mean the morphes are given by graded x's here. Yeah, and step 2 is compute the canonical map in certain. I mean, let's say compare maps for xk, which is the usual map to prioritization of the dual space of one forms, and for Fukaya category. But here there's some obvious cohomological interpretation of canonical map, and you can directly check that they give the same result. And step 3 is using Polishuk's result deduce existence of some curve x prime over k such that probably singular, such that perfect complexes on xk prime are equivalent to perfect complexes over our Fukaya category. And then step 4, which is the simplest, is to show that xk is isomorphic to this x prime k. So first, I will probably sketch the first part. Namely, obviously, when you consider Homs between vector bundles, you encounter theta functions in the more complicated form. Theta functions for these free groups on G generators. And I'll just explain briefly how do you get this from this category. Namely, so what to, I can erase. Once again. Well, I will comment on this. It is some kind of general result that if you have a generator for which the graded algebra of x has some concrete form, then it is necessarily derived equivalent to some curve. Which is in his paper, moduli of curves as moduli of infinity structures. What I want to briefly comment about is how do you construct quasi-isomorphisms from Floer complexes from LE, L prime, A prime, to actually to R Hom in the derived category between corresponding vector bundles. It is the idea is the following. It's actually to obtain this R Homs, they're quite complicated. So there are some even if you do it for line bundles, there are some jumping loci for the cohomology. So it's not an easy task in general to compute this. But actually, what we can do is directly obtain a quasi-isomorphism between this Floer complex and Čech complex, computing this R Hom for some affinoid covering of our for certain covering by affinoid domains, and roughly the idea is the following. So when we so suppose that we have our two Lagrangians. Suppose that in some sphere the intersection is the simplest possible, so there's only one point of degree 1 in the interior. Then what you want to do is basically when you do a Hamiltonian perturbation, the Floer complex doesn't change up to quasi-isomorphism, and you can do it in the following way. Namely, first, so we fix. So this is L prime. This is L. So we fix L prime and don't move it. But for L, we do a large number of rotations in the counterclockwise direction. So let's say we're doing n capital rotations here, then we come then we start rotating in the opposite direction and do it to n+1 times. And then again rotate counterclockwise and do this n times. And actually, if you take limit n goes to infinity, or well, more precisely, I'd like to write it as n equals to infinity. Then the point is that if you do this in each of the spheres, then the Fourier complex from this Hamiltonian perturbation, let's still assume that there is some symplectomorphism, so phi Hamiltonian symplectomorphism, phi of L to L prime, which I understand well as a certain limit, certain completion of certain limit, or if you wish, we can do it for n equals infinity directly. Then this will be just directly the Czech complex. Yeah, if we put here local systems, this will be the Czech complex computing Czech complex for the local home from F to F prime. But Czech complex for certain covering of our curve, namely what happens here is actually the following. Which covering do we use? So first of all, let us notice that when we take first forget about affinoids and let's just take the functions on the projective line minus the distinguished points, minus the 3 distinguished points. Then it has a basis formed by the unit and the negative powers of our chosen coordinates. Which is easy to see. In fact, these negative powers will correspond exactly to this huge collection of points of degree 0, which we obtain as intersection in the lower half sphere. And similarly here, the points which we obtain is intersections in the upper half sphere. And now what we do more precisely for our to get a covering of our curve, we're choosing some we are basically choosing some constant between 0 and AE for each edge. For example, just AE divided by 2. And we take the covering, so affinoid of xk is given by the following. So on each for each v, for each vertex, we're taking a subset uv in this yv, which is given by conditions that for each of the half edges, the absolute value is greater or equal than e to the power minus ce. Well, I just recall that I've chosen the valuation in such a way that absolute value of t is e inverse. Yeah. Well, once again, what? Yes.
Is it the generators or just the Lagrangian manifold of each sphere?
Each Lagrangian should be either. I mean, all the Lagrangians are connected, and either it is just smooth, which means that it is a circle, or it has component in each of the spheres, and this component is a segment. I mean, just a segment connecting the singular points. Yeah. Once again. Yeah, and I'm considering. I mean, just to define an object, I need for each of the spheres, I need a segment, a line from this. All in each of the spheres. So something here, something here, and something here.
So can you think of each line segment separately?
No, only together. Yes, I mean, when I'm talking about local systems, I'm just talking about local system on this topological space. I mean, on this graph, on this configuration. So. Yeah. Okay, so so for each v, I'm taking this open subset, and it projects to some let's say wv in xk, and my negative powers of the coordinates corresponding to these half edges and the unit, they now give a topological basis for analytic functions on each of these affinoid domains, and their intersections are when you consider intersection, they actually given by they're actually given by the equation that absolute value of the coordinate equals to CV, which is just the boundary of the ball, of the closed ball in the fine line, and this collection of intersection points, which is 2n plus 1, but n is infinity, so it is somehow positive, 0, and negative. They correspond just to the all integer powers of this coordinate, which give also a topological basis. And actually, this Floer complex for this somehow limiting configuration, it gives exactly the Čech complex computing home between vector bundles, which can be checked directly, and theta functions arise here when you write down explicitly the quasi-isomorphism between the Floer complex of your initial pair of Lagrangians and this perturbed Lagrangian with this infinite wrapping. When you do this quasi-isomorphism explicitly, you encounter theta functions for this Schottky group. yeah, so I'm just, well, I prefer to avoid explicit formulas here, but just to explain how this works is when you do a perturbation like this. So when you had just a local picture where there is no intersection, and then you do this perturbation where you get two intersection points of degree 0 and 1. I mean, when you construct the Fourier complex, when you construct the quasi-isomorphism between the Fourier complexes explicitly, one of the ways to do this, I mean, the most natural, I think, is so you have CF from L to L prime and CF. So this is L prime, and this is I'm sorry. And this is L tilde, the same L prime. So when you consider these two complexes, you can define the maps actually in both directions, the graded maps from here to here just by sending all the intersection points other than these two to the same intersection point, and projection you define it the same way, but you also have additional operator H here, and this is this operator H is given by H of x prime equals x times t to the power this minus s, where s is this area, and then this is not like the standard amount of data for homological perturbation lemma, for example. So it's not like so this I and P, they are not morphisms of complexes, but to get an actual morphism of complexes, you define I tilde to be the infinite sum over n non-negative h d to the power n I. This gives you explicit quasi-isomorphism between Fourier complexes in this particular case, and you can do this for this the same for this infinite perturbation. And when you write down such summations, you encounter exactly the theta functions. This can be checked directly, and also it can be checked that the products, the compositions agree. This is. I mean, this was needed actually. I mean, we would like actually to avoid such considerations, but we couldn't prove generation of the Fourier category by the expected collections of Lagrangians, because it's kind of tricky to deal with. Yeah. This is how you get such equivalence. I mean, sketchy, and then so. Okay, I'm out of time, but I'll just say that how do you get some abstract curve x prime for which the category is equivalent to the Fourier category is you're using the following result. That if you take x to be some actually any curve of genus G, I mean smooth, proper, connected, and you take collections generating objects, generating collection of objects, structure sheaf, and the collection of skyscrapers at G points, P1, etc., Pg, generic, so that H1 of O P1 plus pg equals 0, then the Ext algebra of this generator, if this is say F0, Ext algebra of this object, if you forget about the infinity structure, but remember only about M2, it depends only on the genus and on the base field. Actually Polishuk result implies that whenever for any infinity algebra A, such that homology of A is isomorphic to this particular algebra, there exists some reduced, I mean geometrically reduced proper curve y such that over k such that the perfect complexes on y are equivalent to perfect complexes over this infinity algebra. And in the Fukaya category, after I know this equivalence of graded categories between for semi-stable vector bundles and the corresponding objects, I know that actually I have a generator of this form in the Fukaya category. Namely, I'm taking my L0, which corresponds to the structure sheaf, and I'm taking any generic collection of circles. So taking L0 and L1, etc. These are just some circles. Generic collection, and this is a generator of for which the Ext algebra is exactly isomorphic to this EG. And then, if I know that this object generates the category, so if I know that this is generators, then I deduce that there exists some curve y with these conditions such that perfect complexes over y equivalent to perfect complexes over my Fukaya category. And then also, I didn't say, but you can actually argue that I mean, the first homology of the structure sheaf for this curve is exactly the same as for our xk, and you can argue that the image of the canonical map is the same, and from this you can actually deduce that the curves must be isomorphic. Yeah, so in this whole story, maybe the most confusing part is the definition of the Fukaya category, this requires some motivation. But I would like just to say that this propagation data maybe it looks weird, but it's local. It's described only in terms of this singular points, and the resultant categories actually give. I mean, you can prove homological mirror symmetry for any configuration corresponding to the generalized Tate curves. Okay, so I think I'll stop here. This curve, yes, it's unique. Yes, only one curve. Yeah. Well, to be more precise, I mean when you, it's more natural also to consider tangent directions at each of these points. Yeah, and he proves the isomorphism of certain modular spaces, which are in the assumption of that characteristic is not equal to 3. These are just affine spaces. So moduli functors are representable by the same. I'm sorry, by the same affine variety, not affine space, affine variety. if you consider on one side, you consider curves with these conditions and with fixed tangent directions, and on the infinity algebras, you consider just infinity structure and fixed isomorphism between cohomology and this particular algebra. I mean, you can define the moduli functor just by considering everything over some K algebra. No, it's not MGN. It's not MGN. It's different. It's not compact. I mean, it's not MGN. It's not MGN bar, and it's not sticky because after you fix this tangent direction, it becomes.
There is some way of, in fact, is there any way of some kind of doing real blow up of those singular points and separate?
I'm not sure about this. Again, locally it's just critical locus of the function xyz on C3, I mean, actually, justification of this definition reduces to the local case, the mirror to the pair of pens, which is this. Yeah, and I thought that the new rule has some conceptual explanation, but I'm not sure yet about this.